We present our model VIRDO, a visual-tactile implicit representation of deformable objects. Despite their prevalence and importance, deformable objects have received less attention than their rigid counterparts, owing to their inherent complexities in modeling, perception, and control. The research goal of our project is to derive a computationally efficient and generative deformable object modeling that predicts object deformation subject to external forces and is compatible with common robotic sensors. At a high level, VIRDO decomposes object representations into a pointwise deformation field and nominal shape representation. The nominal shape of an object is a geometry it takes in the absence of external contact forces, where the shape itself is represented as an implicit function. What VIRDO does is to predict object deformations by learning it as a function of externally applied forces and their locations obtained from common robotic sensors. VIRDO can accurately learn the 3D geometry of nominal and deformed shapes seen during the training. As seen in this figure, it accurately fits surface curves and details at sharp edges. Given the same contact locations but given different reaction forces, our model outputs unique deformation fields to make a unique deformed geometry. We emphasize that VIRDO uses only one neural network model for the entire dataset, containing 6 different objects with 24 deformations each. With our loss function, VIRDO can infer dense correspondence without explicit supervision. For this figure, we first paint the nominal shape, then apply a variety of contact formations and track the painted points. Maintaining dense correspondence is important for tracking a pose and relative deflection of a specific point during robotic task execution. VIRDO can be generalized to unseen contact formations. This functionality is important for robotic applications given the wide variety of contact interactions. Given unseen contact location and reaction force, the model can predict the deformation with high accuracy. Here we present the network details of VIRDO. We assume the object geometry is described by its point cloud P, contact locations are given by Q, and net reaction force is given by U. Then we derive a continuous and implicit representation of deformed object geometry in terms of sign distance function, where the output S is the sign distance from the surface. Deformed object geometry is given by the zero-level set of the implicit function. We define the object model as O and the object code as alpha, where the purpose is to allow VIRDO to represent multiple objects' nominal shapes. Here we use hypernetwork Psi-O to decode the object code into a subset of the object model parameter. To this end, we split the object model layers into shared layers whose parameters are common to all objects, and tailored layers whose parameters are specialized to objects via hypernetwork. The next step is to extend our nominal shape representation to capture object deformations due to external force or contact. VIRDO uses 2 main components to model deformations. First, it summarizes external contact locations and the reaction force as force code Z using the force module F. Second, it uses the summary to predict a deformation field using deformation module. We define the deformation field as a 3D vector field that pushes a deformed object back to its original or nominal shape. The deformation model is conditioned by a concatenated latent curve pair, alpha and Z, to capture the underlying object-specific deformation behavior. This results in different deformation fields for different objects, despite similar contact location and reaction force measurements. So the zero-level sets of X to S becomes the representation of deformed object. And zero-level sets of X bar to S becomes the representation of nominal shape. The performance of the model is quantitatively analyzed in the left table. Chamfer distance, or CD, is evaluated by measuring distance between ground truth point clouds and reconstructed objects using Marching cube algorithm. The L1 loss tests how accurately the model fits zero-level sets by evaluating 800 unseen on-surface points for each deformed scene not used for training. Table on the right shows that the average reconstruction accuracy on the unknown contact formations is within 1 to 2% of the known object, suggesting that VIRDO effectively generalizes to novel contact formations. To further analyze the generalization property of our model, we tested interpolation and extrapolation of force codes, where the number 1 to 5 indicate tested force code and corresponding reconstruction results. The interpolation and extrapolation of force codes bear smooth and even reconstructions. Also, it shows similar results of direct inter- or extrapolation of two given deformations. This implies that the latent space is continuous and complete with semantic meanings. To understand the structure of force and object codes, we visualize these embedding spaces using U-map projections. When visualized on their own, object codes exhibit significant separation. Force codes are naturally distributed according to the band, which suggests that the force code naturally clusters similar contact formations to more effectively generalize across objects. More importantly, the model learns to cluster latent features by deformation properties that are not directly observed or given as input.